Okay, morning everyone, or evening, or whatever it is. It's the morning for me. Um, so this is the part one of the last topic for the course, which is learning about the analysis of variance, or what we call ANOVA. And so we're going to split this into two parts. In this lecture, I'm going to talk about some of the concepts and illustrate some of the math involved in performing this. And then there's a companion lecture where we have Excel do the analyses and we focus on interpretation. So much of this stuff, the concepts and the math, well, at least the math will be performed by Excel, but it can help illuminate some of the concepts. So the analysis of variance is a procedure that is different from what we've done before. And it's useful to analyze data from experiments that employ more than two groups or conditions. So it can also be used for analyzing two conditions, but we tend to use it for more. And the reason that we do so is because if we were to use t-tests to compare all these groups to one another, we would end up raising the type 1 error rate over 5%. And it's just generally an inefficient procedure. However, what it requires, analysis of variance, is to slightly reframe the issue that we're looking at. So with t-tests, our main question was whether or not two groups of observations differed with respect to their mean score, the average from the groups. With analysis of variance, instead, what we do is we ask a question, well, does the thing that makes the groups different, which is the treatment or the independent variable, does that contribute to the variability of people's scores? Basically, does that lead to an effect on scores being in a particular group? And so the way that we analyze that is we split the variation in people's scores into what we call two sources of variance. The between groups variance, which is the variability in people's scores that may be due to differences between treatment groups or the different conditions under which we measured them. And then what we call a within groups variance, which is essentially a pooled variance, as we did with t-tests. It's an estimate of variation of the scores without respect to treatment. So this is rather abstract, and it is a change from what we've been used to. So before we get into it, what I want to do is I'm going to give you an example of a type of design in which we would use this analysis, and then we're going to walk through the conceptual components of it, and then make our conclusions. So suppose you're interested in determining whether different situations produce differing amounts of stress. And you know that the amount of cortisone, or corticosterone, excuse me, circulating in the blood of humans is a good measure of how stressed a person is. So what you do is you do an experiment. You randomly assign 15 students into 3 groups, and each of these groups have 5 students each. The students in group 1 have their corticosterone levels measured immediately after returning from vacation. So let's say after returning from spring break. The students in group 2, they have their corticosterone levels measured after they've been in class for a week. So they're back and it's moderate stress levels. Whereas students in group 3, their corticosterone levels would be measured immediately before the final exam. So the question is, well, how should we evaluate whether there's an effect of stress on corticosterone? How should we do that? Well, let's first look at the data. What we've got is, again, we've got the vacation group, we've got the group that has had a week of class, and the group that is measured during final exam. So as before, the X values are the levels of corticosterone. So these are just integer values representing some proportion in the blood. So what's important is, as we did with t-tests, we can average together people's scores in each group, and we see that the vacation group has a mean of 4 for the corticosteroid level. The group that has been to class for a week, they've got a mean of 8. And the final exam group, the group measured right before finals, has the highest mean. Right? So we can see that the groups clearly, in terms of the average corticosteroid levels, there's a difference. So clearly, right, this group is lowest, medium, high. The question is, well, how do we determine or do a statistical test of this difference? Um, Again, if we used t-tests, what we'd have to do is we'd have to do 3 t-tests. We'd have to compare group 1 to group 2, group 2 to group 3, and then group 1 to group 3. That brings up our false positive rates. But there's another thing that we can do, which is that you can see, right, all the scores are different. And what the squared scores here are setting up is, if you were doing this by hand, you would essentially want to compute sum of squares for each group. You're not going to have to do that, but essentially the point of that is that there are these what we'll call between group variance, which is essentially a function of how different the group means are, right? If they're different numbers, then they're more variable. And variance is a measure of how distant a set of numbers are from each other, right? So the further away these means are from each other, the more variance there is across the groups. But we have to compare that variance to what would happen if we ignored group assignment. So the crux of analysis of variance is to get a measurement of variance of scores that have something to do with being in a particular group, and compare that to the variance of people's corticosteroid levels without respect to what group they're in. Right? And so, again, this is just kind of stating it again. And the important point is, if there's more variance in the group means, so if the means of each group are more variable than might be expected relative to how variable the scores are, then that variance in the group means must be due to having been in a particular group. So this sets up a null hypothesis for us to test, which is essentially that the population means that the groups represent, so low stress meaning they're coming back from vacation, medium stress meaning they've been in class for a week, and high stress the exam. The null hypothesis for an ANOVA can be stated in this way, that all 3 groups are equal in their mean stress level. Now, that's kind of a simplistic way to say it. What we're really saying is that there's no variation between these means, that they're all essentially similar or the same. So that ends up being our null hypothesis for analysis of variance, is that it's similar to t-tests, that all the group means are equal to one another. But since we have more than 2 groups, we can't talk in terms of mean differences anymore. Now we have to talk about variability, because we have more than 2 means to compare. So what we do is we compose a ratio, and this ratio is called the F ratio. And F is like T. It's a test statistic. It's a statistic that we calculate, that we use to test the null hypothesis. And so it's a ratio of 2 estimates of sigma squared, which would be the variance of people's corticosteroid levels in the population. So we form 2 estimates of it. One that takes into account any between group variation, so any variation in corticosteroid levels that have to do with having been at a different point in the semester. And then the within groups estimate of sigma squared of population variance in corticosteroid levels that is not with respect, that's averaged over the groups. So again, we call this the group between groups and the within groups estimate of variance. And analysis of variance is essentially just the process of calculating these 2 estimates of sigma squared, and then dividing one into the other to get our F-test statistic. So the mathematics involved it's not terribly complex, but again, we'll let Excel do the work. This is just to illustrate to you the concept of what we're doing. We're now essentially, the idea is that as the numerator, as the between groups estimate of variance gets larger relative to the denominator, that means that there's more effect of the grouping variable. So in this case, there's more effect on corticosteroid levels uh, uh, based on what time in the semester you were measured. In analysis of variance, we call these two estimates mean squares. Right? And the way that we do an F-test, actually we'll use a p-value. There's a critical value method. I'll explain to you the p-value, but this is basically just saying that we would like to have this, our F-test statistic, to be a large number. If it's a large number, that means that the mean squares between groups, which is just the estimate of the between groups variance, is very large relative to this within groups variance estimate, which is just a pooled variance of all the variability across the groups pooled together, so averaged over or marginalized over group membership. So I'm going to show you how these are calculated by hand, just to show you, again, how the different sources come together. But we're going to let Excel do that for us. The important point, though, is, again, this is your final test statistic. It's the F-test, or the F ratio, that we then derive our p-value from to compare to alpha. So before we talk about that, let's just kind of schematically look at the process, the sort of conceptual process of what we're doing. So the technique, right, is that, so in our example, we have 15 people, and we've measured corticosteroid levels from those 15 people. So at first, we're going to ignore what group they're in. And we can compute the total variability in terms of sums of squares. So we could take all 15 scores and compute sums of squares with the formulas from chapter 4. From there, our next step, and what Excel will do, is it will take that total sum of squares number and split it into two parts. One, which it represents the sum of squares between groups, which we turn into a variance, essentially a variance of the group means. And the other part turns into our estimate of the variance across scores, across different groups. And the important component here is that we're taking all the variance and we're splitting it into two parts. And so we could put it back together into one total. And then at the end, right, this process, this partition, the between groups partition, forms the numerator of our F ratio. The within groups partition forms the denominator of our F ratio. And then we divide, these are two numbers, two variances. We divide them and we get an F test. So what do we do with that F value, the value of the F ratio? Well, it turns out that we can derive a probability distribution for the F test. And you're looking at it right here. It is a skewed distribution because it's a variance can never be negative. So an F value can never be negative. And in fact, you're most likely to have F values in and around 1 because that would represent a situation in which there's about the same amount of variance between the groups as there is within the groups, which represents the null hypothesis. So if the null hypothesis is true, you should have an F ratio of around 1. As F gets larger, what that means is that you've got more and more variation in your data that we can attribute to the grouping variable from having been in a different group. And so there's a certain point on the F distribution in which our p-value would equal exactly 0.05. In some situations, we call this the critical value. But since Excel gives us p-values exactly, we're going to essentially, Excel will compute an F value. F can get very large, as we'll see. F can be 20, 30, 40, 50, 100, really can get as large as it wants. And the p-value is just a one-tailed p-value. The f-tests are one-tailed tests. But you will do the same thing. You will compare your p-value to alpha, and the smaller it is, the more surprising your result is under the null, or at least the smaller the p-value, the more likely you are to reject. And so, for example, we can use 0.05 or 0.01 as our alpha level, and we'll do the same thing. We'll reject a null hypothesis if our p-value is less than alpha. One thing that's going to be important is we introduced degrees of freedom in the last chapter on t-tests. And degrees of freedom come from the fact that we have to estimate variances based on our data. And so, in fact, the F distribution involves two different types of degrees of freedom. It has 2 degrees of freedom parameters because, in fact, it is actually a ratio of 2 distributions of variance, each with their own degrees of freedom. What's important is that, again, Excel will compute these for you, but it's important to know what they represent. So the between groups degrees of freedom is always equal to k, the number of groups that you have in your design, minus 1. So in our study, we have 3 groups, so our between groups degrees of freedom would be 2. This distribution illustrates a design in which we would have 4 between groups degrees of freedom, meaning we'd have 5 groups. And this is what the F distribution will look like. So similar to the T distribution, the F distribution sort of stretches out and squishes down depending upon the degrees of freedom values. It ends up being skewed in the way that you see it like this, but it can kind of get stretched or smushed depending upon what the degrees of freedom values are. And these come directly from our design. So the first number, the smaller of the two, is a function of the number of groups we have. And the second number is a function of the number of observations we have and the number of groups we have. So big N is going to be the total number of observations across groups. So little n represents how many people are in each group. Add them together, you get total. Now we're going to deal with designs in which we have an equal number of people in each group. Because if we don't have that, then the formulas become much more complex. So big N is just little n times how many groups you have, or you can count up the people. So in our design, we have 15 people. Big N is 15. And K is 3. So we would have 12 within groups degrees of freedom. Okay. So I want to walk you through a few things. As you can see, here's our data. I've computed sums of squares. And by the way, again, Excel's going to do this, but I think conceptually it's nice to see what happens. Again, we need an F ratio is comprised of of 2 mean squares. Well, one is called our within groups mean square, MS within, and simply what that is it's a weighted average, or it's really an average of the sums of squares, it's an average of the variances. It's a weighted average of variance. The way that we would compute that is we would compute sums of squares for each of the groups measured after vacation, after class, after the exam. We have the sum of squares there. And then we would form the degrees of freedom within each group, which is just the number of people, 5 minus 1, so 4, 4, and 4. And the math is simply add the sums of squares together and divide by the total within groups degrees of freedom. So that's 54 divided by 12. So the denominator of our F ratio for this problem would be 4.5. Now, again, you'll see this in the Excel output, but this is how it's computed. The mean squares between is very difficult. Essentially, what you have to do is it needs to be an estimate of we need to derive an estimate of the variance of a distribution of means. And that gets a little bit complex because it has to do with the number of people in each group to get a sums of squares. So functionally, what's done is you can actually compute it simply by taking the variance and multiplying the number of people in each group. So the variance of the group means, if we do it the easier way, or more straightforward way, is we would take the difference between the first group's mean 4.0 and what we call the grand mean, which is the average corticosteroid levels across groups, 8.33. So we would do that, square it. We take the second difference, square it, the third difference, square it, divide by the number of groups minus 1, and we get the variance of the group means. If we multiply that by 5, we get that's our sample size within each group, we get our mean squares between. So our mean squares between is 101.67. And so putting that together, if I divide those two numbers together, I get 22.59. That's my F test. Now, there's a second way to get each of these numbers, which is to first compute the sums of squares and then divide by degrees of freedom to get variance. But again, Excel's going to do all of this for you. So it just kind of looking at what's going on to get a little bit of insight. What is important to recognize is the steps are really to start by computing this number, the total sums of squares, 257.333. Again, that's the sum of squares across, in this case, all 15 scores. From there, there's actually formulas for splitting it into these two parts. If you notice, if I add 203.333 to 54, I get 257.33. So these two numbers, the between group sums of squares and the within group sums of squares, represents two parts of this 257.333. So we're partitioning this set of this number into two parts. And then once we do that correctly, if we divide across, so 54 divided by 12 is 4.5, 203 divided by 3.333 is, or 203.333 divided by 2 is 101.667. This is called the ANOVA summary table, and it is often given by statistical programs because it's it's good to be able to check your errors and make sure that things look the way they should. And the end result is this is how we compute our F ratio. So a couple things. Our F ratio is very large. And then the question is how large is it? How large does it need to be for us to reject the null hypothesis that that there's no effect of the time of the semester on corticosteroid levels? If we look at what Excel gives us, and again, I'll explain how to get this in the other part 2 of this topic, we're going to use the regular old p-value method. The book teaches you the critical value method in case you don't have a computer, but we have computers. So the important component is to notice, okay, what Excel gives you is it gives you the F value. Notice it's all the same numbers. It computed it correctly. And then next to it, it gives you a p-value. So this is the normal p-value that we've been used to. It's only a one-tailed p-value, but we don't need to do anything to it. We want a one-tailed p-value. It's the only one that makes any sense. One note, though, you can see this is a strange-looking number. Excel uses exponential notation anytime it's got a number that's very small. So this reads 8.5386 E negative 05. What does that mean? That means multiply 8.5386 by 10 to the negative 5, which means move the decimal point. You move the decimal point to the left 5 times, and you get 4 zeros and then an 8. So if we had alpha of 0.05, our p-value for this f test is 0.00008 and change. Clearly, our f value is much less than 0.05. And again, what does that mean? What does a large f value mean? A large f value means that there is much, much more variation in people's corticosteroid levels attributable to the group that they were in, or in this case, the time in the semester, than there is just without respect to that. So a large f value illustrates that our grouping variable, the independent variable, is likely having an effect on people's measurements. In this case, we're measuring corticosteroid levels, right? And so we say, well, this is a significant result. We can reject the null hypothesis because our p-value that goes along with this f, large F, goes with small p. And when p is less than our alpha level, if it's 0.05, we reject the null hypothesis. And that would be our decision here. Because again, it's in that strange notation. And any time you see a number followed by e to the negative 0 something, that's usually a very small number. Okay. One other issue is we would like to compute effect size. We would like to give some standardized estimate of the size of the effect of our independent variable. But Cohen's d is no longer useful because Cohen's d is a difference. That's what d stands for. Instead, what we're going to do is we're going to use the fact that analysis of variance is very similar to regression in the sense that both are versions of what we call the general linear model. And all that means is that we can use a variant of r squared to quantify the effect size in an analysis of variance in ANOVA. So effect size in ANOVA is going to be interpreted as we did in chapters 6 and 7 as the proportion of variance in the dependent variable scores accounted for by the independent variable. So in our example, effect size would be the estimate of the proportion of variance in corticosteroid level, or dependent variable, accounted for by external stress level or time in the semester, which we expected to go with external stress. So there's a couple of different variants on effect size for f-tests. We're going to learn one called omega squared or little omega squared. It looks a little nuts, but the important thing to notice is that if we look back to our ANOVA summary table, this is a little bit of a cleaner look at it. We've got sums of squares, degrees of freedom, and mean squares, and we've got two sources along with the total. That's helpful because we will use those numbers in a particular combination to compute little omega squared. The result of this computation, you really want to watch your parentheses. The result of this computation can never be a number larger than 1, right? It's a proportion. So what you're computing is actually the proportion of between groups variation relative to the total variation. And then the rest of this is a correction for some of the bias that direct computation would lead to. So this makes it a little bit more accurate in projecting up to the population. Right? Now, k-1 is not necessarily in the table, but it actually is. It's the degrees of freedom between groups. K, in analysis of variance, represents the number of groups that you have. Right? And so we have 3. So we already know this number is going to be 2 right here. And we're going to pull out sum of squares between, mean squares within, sum of squares total, and then same number there, here. Right? That's not a mistake. They go together. We just pull those out of the table and we do the computation. So from our table, sum of squares between is 203.333. We put that there. K-1 is 3 minus 1 is 2, also known as the between groups degrees of freedom, 2. Mean squares within is 4.5. It's right here. slot that in there. So we do that computation. That ends up being 203.33 minus 9, or 194.33. So that would be our numerator. This works out to 193.33, that top. The denominator, we take the sum of squares total, 257.33. We add to it the mean squares within, 4.5, right? And we end up with 261.83. That's our denominator. We divide those and we get 0.74. So little omega squared for our corticosteroid level example is 0.74. That's a proportion. We can interpret that as a percentage. So we can say that 74% of the variance in corticosteroid levels in our experiment can be accounted for by the changing external stress conditions. So essentially we're saying 74% of the variance in people's corticosteroid levels can be accounted for or explained by the different, essentially the group that they were in. What time in the semester did we measure that? Now that sounds like a causal statement. It can be if we've controlled the experiment well enough, but it's still really akin to an associationistic statement. So just because we say something accounts for variance in something else doesn't mean we're saying that, you know, their corticosteroid levels are definitely caused only by external stress. Obviously, there's going to be other things, but this is a way to indicate you know, just how much variation we can attribute, or the size of the effect that we can attribute to the independent variable. And of course, across different studies, let's say you found in the literature that there are like 20 different studies in which corticosteroid levels were measured in students at different times in the semester. Well, you could compare, if each study provided you a way to compute or computed directly little omega squared, you can compare those across studies. You could actually get an average across studies of little omega squared to estimate sort of a collective effect size. All right. So the way that we summarize results from analysis of variance is we would simply, you know, state whether the effect of the independent variable is significant or not. Okay, so that's akin to rejecting or do not reject. And then our notation is given right here. We make a capital F, and in the parentheses, we're giving the between groups degrees of freedom, followed by the within groups degrees of freedom in that order. What that's doing is it's telling the reader, this is an F value right here following it that comes from, and we're going to evaluate the probability of this F value to 22.59 using the particular F distribution that gets its shape from the 2 degrees of freedom parameters. So on that distribution, the right-tailed probability, the probability of obtaining an F at or greater than this is 0.000, actually it's a typo, there's one too many zeros in there, but you can check the previous slide, and then we add that effect size. Now in APA style, often what we do is we pick a number, alpha or something else, and we would just say P is less than that point because it's very, very small here. So it's up to you how you want to report it. Then what we would do is use a paragraph form similar to what you do with t-tests, and you list means and standard deviations. And I'll show you a little bit about that in the next lecture. Okay, so this is just a lecture on the concepts of analysis of variance, and show you some computations, just so you some people may find some deeper understanding about that. If not, that's okay. The next and final video is going to take you through the steps to get that ANOVA table in Excel, and then writing it up, and then a little bit of an additional thing that we'll want to do for any design in which we have more than 2 groups. So we'll see you when we get to that lecture.